Good day, everyone. I'm Carlo Tan, who will be your discussant for today's video. Our lesson is all about the related rates. And here's our objective on related rates. At the end of the lesson, the learners must be able to first define a related rate and solve situational problems involving related rates. So let's define related rates. So, according to Rosen et al. 2016, when two or more quantities vary with time and are related by some condition, their rates of change are also related. And also, in general, a time rate of change is if V stands for volume that is changing in time, then the limit of delta V over delta T as delta T approaches Q is equal to the derivative of V over derivative of T is the rate of change of the volume with respect to time T by Costales et al. 2021. So let's have an example about the related rates. So let's consider the situation of an inflating balloon. So as you can see in the video, the balloon is widening, or the size of the balloon is getting bigger. Also, if the balloon is getting bigger, then the length of the diameter increases. Additionally, when we talk about the balloon, the volume of the balloon, it also increases. Therefore, when inflating a spherical balloon, the volume increases as the diameter also increases. So, when a spherical balloon is inflated, there is a relationship between the pace at which the diameter changes and the rate at which its volume varies over time. And also, a related rates problem concerns the relationship among the rates of change of several variables with respect to time, given that each variable is also dependent on the others. Particularly, if y is dependent on x, then the rate of change of y with respect to t is dependent on the rate of change of x with respect to time or t. That is, the derivative of y over the derivative of t is dependent on the derivative of x over the derivative of t. Now, the steps in solving related rates. So we have first, define the variables. Second, let's write down the rate that is provided in the question. Third is we have to establish the relationship between the variables. Number 4, write down the rate that needs to be found. And lastly, use chain rule or implicit differentiation to relate the variables. So let's have an example. Number 1, a circular metal plate is being heated and its radius is increasing at a rate of 2 mm per second. Find the rate at which the area of the plate is increasing when the radius is 30 mm. Number 2, a spherical balloon has a hole in it and the balloon's volume is decreasing at a rate of 2 cubic centimeter per second. At what rate is the radius changing when the radius of the balloon is 4 centimeters? So example number 1. So first, we have to define the variables. So we have r is equal to 30 mm and dr over dt is equal to 2 mm per second. We all know that from the given, the radius is increasing at a rate of 2 mm per second. Next is that we knew that the plate is circular. Therefore, the formula for the area of a circle is A is equal to pi r squared. So we have to find the rate at which the area of the plate is increasing with respect to time. Now, we form a chain rule for the required rate in terms of the variables. So we have dA over dt is equal to dA over dr times dr over dt. So now, we have to recall a certain formula when it comes to geometry. We are talking about the area of the plate or the area of the circle. And we knew that the plate is a circle. So the area is equal to pi r squared. Now, to get the dA over dr and also dr over dt, which is needed because the radius is given, we have to get the derivative of the area of the circle with respect to time. So we have dA over dt is equal to pi r times dr over dt. Next, substitute dr over dt, which is 2. So we have dA over dt is equal to 2 pi r times 2. And we have dA over dt is equal to 4 pi r. And we have r is equal to 30 millimeters. Then we have is equal to 4 pi times 30. Then we have a final answer of 120 pi. Therefore, the area is increasing at 120 pi millimeters square per second. So example number 2. So we have here the given as r is equal to 4 centimeter, and we have the change in volume over the change in time is equal to negative 2 cubic centimeter per second. So as we all know, a spherical balloon is also a circle. So we have V, or the volume, is equal to 4/3 pi r cubed. And we have to find dr over dt, or the change in the radius over the change in time. So we have here dr over dt is equal to dr over dv multiplied by dv over dt. So take note, we have the volume of 4/3 pi r cubed, so we have to get the derivative. So we have 4 pi r squared. But wait, the given is dr over dv, so we have to get the reciprocal of it. So we have 1 over 4 pi r squared. Next is we have dr over dt is equal to 1 over 4 pi r squared times the dv over dt, which is negative 2. So we have dr over dt is equal to negative 1 over 4 pi r squared times r. So our r is equal to 4. And we have dr over dt is equal to negative 1 over 32 pi. Therefore, the area is decreasing at 1 over 32 pi centimeter per second. Thank you.